Okay, today we will continue with the discussions of the previous lecture on two phase asymmetrical induction machines with the rotor being squirrel cage. What we did was we consider that if M and A windings which are asymmetrical, they carry currents I m and I a with applied voltage V m and V a. If single winding is excited, that is the main winding is excited with the current I m, it will produce a forward field and a backward field, and it will induce a voltage both in the M and A winding. So, M winding voltage applied voltage will be counterbalanced by the induced voltage in the winding plus the series impedance drop. Okay. So, that is one equation you write, but the same field will also induce voltages in the auxiliary winding, okay, which will be displaced by the main winding by 90 degrees plus or minus depending upon whether it is by forward or backward field, and it will not have a magnitude which will be different than the main winding because the number of turns are different. Okay. So, if the main winding the same flux will produce a voltage V, in the auxiliary winding it will produce a voltage A into V, because it is suppose it will have a times the main turns. So, we could get the necessary voltage equations, okay, and if one winding is excited, this is what will happen. If the second winding alone is excited, then it will produce a similar type of voltage equations, both on the, if the auxiliary winding is excited, the voltage applied to the auxiliary winding will be counterbalanced by the drop in the auxiliary winding, series impedance drop plus the induced voltages due to its own forward field and its own backward field, but these fields will also produce induced voltage in the other winding, that is the main winding, which is at quadrature lagging, and they will be displaced by 90 degrees, but it will have a voltage which will be 1 by A times what it would have induced in the auxiliary winding. Okay. Now, if both of them are excited, if A and both M and A windings are excited, carrying a current I m and I a. So, you can imagine that all of them will produce cumulatively one forward field and one backward field. So, the magnitudes of course will not be different, will be different, okay, depend on the magnitude of I m and I a, and so a net forward field will produce a net forward voltage in the main and auxiliary winding, net backward field will produce a net backward voltage in the main and auxiliary winding. Okay. So, you can imagine a cumulative effect like this. So, that is what we have done in the last class. Okay. So, we have the V A and V m with I m and I a. Okay. And we also said that if the A is N A by N m, last class we say that it will produce in main winding EMF I m Z f by 2 E m b with only main winding, okay, and we have the Z L m which is R m plus J X L m, and we said that if the auxiliary winding voltage is induced, if the main winding is excited by these terms, okay, and we also said if only A winding is excited, it will produce a forward voltage in A winding, backward voltage in A winding. It will also produce forward voltage in M winding and backward voltage in M winding given by these equations. Okay. Then we say both of them are excited, we say E m in the main winding will be given by the forward field of the main winding, forward field of the auxiliary winding, backward field of the main winding and backward field of the auxiliary winding. So, all these voltages will be induced in the main winding. Similarly, in auxiliary winding it will be induced in the same main winding it will be the forward voltages will be a cumulative effect of I m and I a, backward voltage will be a cumulative effect of I m and I a. Okay. And auxiliary winding also similarly it is due to cumulative effect of I m and I a and cumulative effect of I m and I a due to backward fields, right. Then we define what is known as, we can call it as the forward voltage V s f by this transformation V m minus j V a dash and backward voltage V m plus j V a dash. right. And then we similarly you can have ESF, ESB, ISF, ISB with similar type of transformation. Okay. And then we said that well, this is the turns transformation VA, what is VA dash, IA dash, ZA dash. Okay. This is referring the rotor referring the auxiliary to the main turns. Okay. Then from this set of equations we said VSF will be ISF ZF plus ISF into ZLM by 2 ZLA by 2 A square plus ISB into ZLM minus ZLA by A square, and VSB backward will be ISB ZB plus ISF ZLM by 2 minus ZLA by 2 A square and ISB plus this. Maybe I'll try to, maybe we will try to derive this in a little more or a proper way. So, we have said that VSF will be half of VM minus JVA dash. What was VM? ZLM IM plus ISF ZF plus ISB ZB. You go back, sorry. Okay, you know VM will be given by this IM minus J IA by 2, what will be? This will be IMF or sorry ISF, you can say ISF ZF plus ISB ZB, isn't it? This EM, that is the induced voltage in the main winding, induced voltage in the main winding with both the currents will be due to the positive sequence net current and magnitude net current. So, you can try to get that equation. So, ZLM IM plus ISF ZF plus ISB ZB, and we can write VA dash will be ZLA dash into IA dash plus J times ISF ZF minus J times ISB ZB. Okay. This you can easily get it. You know the VM and VA equations, and with these transformations you can have this. Now, you find out what will be the VSF now. Substituting this one will be half of ZLM IM minus J times ZL A dash IA dash. Okay. This is VM, then what will happen? ISF is same, ISF ZSF, if you add this will be VM minus J by 2. What will be this? That will be just ISF ZF, isn't it? What will be other term? What will be this term? What will be the sum of these terms? See, J VA dash will be minus J into J is J square, minus J square is plus 1, isn't it? Okay, you have to minus. So, this will be same. So, this minus this will cancel. So, there is no, for the VSF, the forward voltage, there will be no induced voltage from the backward field. Okay. So, So, if you try to maybe simplify further, VSF will be half ZL M I M minus J times ZL A dash I A dash plus ISF ZF, then VSB will be half of, that is ZLM IM plus J ZL A dash IA dash plus ISB ZB. Okay, you get these two equations, but I would prefer to have everything in terms of ISF and ISB. Okay, but this is possible if you say we know that IM will be given by ISF plus ISB, okay, and IA dash will be J times ISF minus ISB, because you have the relations, you can go back, right. So, I substitute this for IM and IA dash here. Please substitute here. So, this will be VSF equal to half of ZLM ISF plus ZLM ISB, okay, minus J IA dash. What will this be? Because we are trying to have other one minus J ZLA dash, IA dash will be into J ISF minus ISB plus of course ISF ZF. Okay. IA dash I am substituting, for IM it is, okay. So, we have to do a little jugglery. So, we have, if you look at that first term, you have VSF will be equal to half ZLM ISF plus ISB my plus half ZLA dash ISF minus ISB, which you can write it as ZLM ISF minus half ZLM ISF plus half ZLM ISB plus half ZLA dash into ISF minus ISB. So, I am writing it as ZLM ISF plus we have the ISF minus ISB. If you look at this, this will be plus half ZLM into I would put it as minus half ZLM into ISF minus ISB plus half ZLA dash into ISF minus ISB. Okay. this I am taking the first term, of course the last one of course will be ZFIF, is not it. Okay. Now, we are only trying to do a simplification of the same thing. So, what do you get this first term as? This will be you have VSF will have ZLM ISF plus half of ZLA dash minus ZLM into ISF minus ISB plus ZFIF, isn't it? Because what this one is ISF minus ISB into half ZLA dash minus ZLM. This is a common and this is the, is it okay? Right. Now, we define this term as ZD as half of ZLA dash minus ZLM. Okay. So, we have VSF will have ZLM ISF plus ZD into ISF minus ISB plus ZFIF. Okay. That is VSF. So, I can write VSF as ZLM, okay, ZD ISF is it right? I can make this circuit, it is just a simple circuit like a loop equations like that, right. And similarly, if you want to go to what is VSB, we have a similar expression here backward. Okay. So, we that will maybe okay. So, that will also be, you can write VSB will be ZLM ISB plus ZB ISB plus ZD into ISB minus ISF, that will be VSB. Okay. So, we can write the other side, you can have the ZB here, ZLM here, okay, and you have these equations. This will be VSB. Okay. This will satisfy this. What will be VSF plus VSB? V is nothing but the voltage across the main winding. Okay. So, this will be the equivalent circuit of two phase asymmetrical stator induction motor. Okay. Whatever voltage you apply Vm and Va, so it is a very general equivalent circuit, isn't it? Not particular to the any specific case. Okay. And ZD is important, ZD is half of ZLA dash minus Zm. But if it is a symmetrical machine, what will happen? If the two windings are identical, what what will happen? If the two windings are identical, ZD is 0, so it becomes a short circuit, okay, in that situation. But in both cases you have ZLM here. What is ZLM? So, ZLM is Rm main winding plus its leakage reactance JXL main winding, and ZLA dash will be RA dash plus J times XLA dash, okay. And you also know what is ZF? This is ZF, this is JXM, RR by S, JXLR, and similarly you know ZB will be an identical one, RR by 2 minus S, JXLR, JXM, okay. So, I think you know all the parameters, right, and you should be able to now calculate the performance of a asymmetrical induction machine with this. So, you know you can calculate ISF ISB, from ISF ISB you can calculate IMIA, okay, main winding, and you can also find out what is the, this will be IR, IRF, this will be IRB, is not it. So, you have all these equations to governing equations. So, you have VSF is equal to ISF ZLM into ISF ZF plus ZD into ISF minus F. In fact, it is rewritten again. VSB is ISF ZLM, ISB ZLM, sorry, it is written wrongly. This is ISB ZB plus ZD into ISB minus ISF. So, this is what the equivalent circuit it has been redrawn here. So, this will be ISF, this will be ISB, okay, ZLM and this, and you know this, if you say, if you want to expand this here, so this will be okay, same thing here also. Okay. This will be JXM RR by S, JXLR, JXLR, JXM 2 minus S. Please note that there is no, it is not XLR by 2 here, do not confuse with the thing, because if it is a it is not a single phase machine, it is 2 phase machine. Okay. Now, what will be this current? There are 2 currents here, I, R, F. Okay, you can all, when you know ISF, you can have a, you can calculate this, no? Okay, when this is ISF, you can calculate what will be the IMF, that the magnetizing current and the rotor current, and if this is ISB, this will be IRB. What is ISF? What is significance of IRF IRB? What is IRF IRB? These are the currents where? In the rotor. IRF IRB are currents in the rotor due to forward field and backward field. Forward field induces a current in the rotor. In a normal machine, when backward field is not there, there is no IRB. Is it okay? So, IRF are, that means what will be the nature of this? This will also be positive sequence currents in the rotor bars. Okay. Forward field will induce in one way, backward field induce opposite way. Then another thing, what will be the frequency of currents in the rotor? IRF will be what frequency? So, this will have SF frequency here and this will be 2 minus SF. So, if it is a 50 hertz machine, if it is running a 10% slip, so this will be 5 hertz and this will be 95 hertz. Okay. So, there are you will notice therefore, an unbalanced stator will create 2 frequencies in the rotor and both frequency currents will be there in the bars. Okay. One will be nearly DC, another will be double the frequency. Now, when having solved that equivalent circuit, you need to calculate the torque, is not it. So, it is very easy because you have a the PGF, that is the power fed to the forward field into the rotor will be twice ISF square RF. RF is the resistive component of ZF. Okay. RF is the resistive component of ZF and so the torque will be twice because it is all 2 phase model, 2 by omega s ISF square RF, that is 2 by ISF square into RR by S. Sorry, this is IRF square because this is equal to twice IRF square RR by S, because whatever is the power here will be same as the is ISF square RF, is not it. Power here is, what is the power fed here is ISF square into the real part of ZF, that is also equal to IRF square RR by S, is not it. Any doubt on this? Okay. Therefore, ISF square RR by S will be equal to IRF square ISF square RF equal to IRF square RR by S. Similarly, the forward torque will be given by 2 by omega s IRF square RR by S. Now this is about the forward torque. Now backward torque will be PGB, that is the power fed to the backward field from the stator, will be twice ISB square RB, is not it, twice ISB square RB. Okay, this is ISB because this is nothing but RB plus JXB. So, ISB square RB is the power fed here, that is also equal to IRB square RR by 2 minus S. Is it okay? This is same as this. So, ISB square RB is equal to IRB square RR by, I think it is all wrongly written, equation had to be changed, it is 2 minus S. Okay. Yeah. Because it's a 2 phase machine, because it is all twice, isn't it?
Hasn't that been taken care of in the earlier calculations in the model problem?
No, it is
Reflected on the equivalent circuit.
the equivalent circuit is taken as we have taken half of IM plus IA dash. We are not taken, you see it is per phase. ISF, ISB are the per phase of the 2 phase model. Okay. ISF is half of IM minus, see the thing is, supposing ideal condition, if this is IA and this is IM, ideal too, ISF is half of minus, okay, and this is nothing but IM actually in a balanced case. So, this is per phase, is not it, per phase current. ISF is a current in one phase, we have made it as a cumulative because it is that which will produce the field, right. Okay. Now, sorry. Now, net torque will be Tf minus Tb, which is 1 over omega s into Pgf minus Pgb. Okay. So, you are able to now, what you are able to do? So, you are given, what are you given? Vm, Va, slip and parameters. For a given induction motor, you are given the parameters of the equivalent circuit. Parameters means all the Rm, Ra, XLM, XLA, XF, Rm, all these things you should know. Okay. Then from these parameters, you know Vm and Va, right. So, you can know VSF, VSB, right. You know VSF, VSB, okay. Then you find out from this ISF, ISB, okay, and you, right from you go to equivalent circuit, you find ISF, ISB, and from there again you go to IRF, IRB, okay. You can always find out because you know the parameters, okay. Next is you can find out what is the torque Tf Tb, then net torque T, right. So, you can be you should be able to estimate what will be the torque versus speed or slip, is not it. So, it may have some variation for a given Vm and Va. Therefore, I think this will be maybe we will try this will be a project for one of you. So, you can develop a MATLAB program to estimate performance of a two phase machine. Okay. You make a general program, then you can put it to the specifics, right. And let us say what are the specifics, because what are we doing for? We are doing because we have a purpose. What is the purpose is that we know large number of single phase motors operate under two phase mode, though they are not connected in a two phase way, but we want to know how much torque it will produce, okay, at a given slip, right, and how much current it will draw for a given voltage. So, you should be able to estimate the currents in this, and actually not only ISF, ISB, you must also calculate what will be IM, IA. You are interested to know how much current it will draw each of the windings, isn't it? Each of the windings how much current it will draw. So, you have a tool now in with you, that tool is that composite equivalent circuit. You calculate ZD and other things, okay. Now, we will look at the applications of these two phase induction motors now. What are the applications? Okay. We have done all this. Can you suggest some applications where there are two phase asymmetrical machines are used, induction machine, huh? Or what is known, what is the application you know? Huh? Fan is driven by a fan, a ceiling fan is driven by again a two phase induction motor with a capacitor. Okay. There are also smaller ones where you do not use a capacitor, you have a split phase. So, these two types we have already told you earlier, but there we discussed only in a more qualitative manner. Now, you have a tool in where you can estimate and do a proper analysis. So, one is a split phase motor, right. Split phase motor is you have the auxiliary winding and main winding, okay. And the main winding impedance, series impedance ZL M, that means this will have its R main winding, XL main winding, okay. They will have a different impedance and auxiliary will have a different impedance. So, these two are not same, that is what we have in the split phase machine. The main winding impedance is not the same as the auxiliary winding impedance, okay. And obviously, the turns ratio is not 1, invariably it is more than 1. The A, that is Nm by Na by Nm, is generally more than 1. But you have another constant here, Vm equal to Va, is not it, and is the supply voltage. Whatever you have a supply voltage here, single phase supply. So, you connect this same single phase supply to the main winding and as well as to the auxiliary winding, and same thing here. Okay. Same voltage comes across here, there is a V here, there is a V here, right. So, what is VSF here now? What did we define as VSF? Is Vm minus J Va dash, is not it? So, this will be Vm is V minus J A times V, okay. So, you know VSF, and similarly you can have VSB is V plus J times, I think it is half of J times, okay. So, you know what is V, then you find out VSF, VSB, then you find out the performance, okay. Then is it okay? You can find out, then what you know is, then you can find out what is the current I m and the current I a, sorry, I a, I m, and for any given slip you can find out the torque, etc. Is it clear? Any doubt? So, you have the necessary tools, so long as you know the parameters of the machine, so long as you know number of turns, okay. You need to know everything, okay. Then you can find out the current drawn will be, what will be the current drawn by the mains will be sum of the three, this will be I m plus I a, is not it, okay. So, you have the split phase machine, so you can always find out various things like, you can always say this is V, this is I, you can also calculate the power factor. If you know V and I, you can calculate the power factor, you can calculate input power, you know the developed torque, you can calculate the output power, then you can calculate the efficiency of the motor. So, you can have develop the whole program, a computer program in which all this can be estimated. So, you should, whoever takes this project, okay, maybe 2 students can take this project, okay, and they should develop the program, okay, to calculate. So, I wanted one more project you can take is a 3 phase motor with asymmetrical supplies. You take a 3 phase motor, balance supply what will happen, unbalanced supply what will happen, single phase supply what will happen. So, whole transmit characteristic will go on changing, is not it, okay. So, this is one of the thing, okay. So, we can start now identifying the projects, okay. Next, next motor is the capacitor motor, okay. In capacitor motor what will you have? Same 2 phase, okay. What will you have here? you have a in the A winding, this is the main winding. So, what you have is you connect a capacitor here, okay, to the auxiliary winding, rest will be same, you have the same supply, and it will go to the both the windings, okay, same voltage V, isn't it? You are applying a voltage V to both. So, but here the V will be coming across the capacitor plus the winding. So, it will also draw a current I m, I a, and this will be the current I. Okay. So, again you can calculate the performance. What is the difference here? Again ZLM is not equal to ZLA, isn't it? But ZLA includes its own impedance RA plus JXLA, but it will also have minus JXC, it is capacitive. Okay. So, the impedance in the second winding, that auxiliary winding will have, we have to include the capacitance here, and of course, A is not equal to 1, it will be generally more than 1, and Vm equal to Va equal to V, that is single phase supply voltage, okay, no problem. Then you can calculate the torque and voltage efficiencies. So, you can calculate voltage, current, power factor, efficiency, torque, power output, power input, all these things you can estimate. Okay. All you need is the parameters of the machine. Okay. Now, there is one more factor you need to know, that is in whether it is split phase or something, there is always a starting performance and running performance, is not it? Okay. Except in a permanent capacitor case, you may have for example, in starting you can have only 2 windings, and in running you may have 1 winding, this in right. Therefore, your performance program must change. So, here you use the 2 phase model which we have just now discussed, and here you will have to have a 1 phase model. Okay. So, what is likely to happen is, if you have a in starting you will be operating with a 2 phase model, and suddenly you have a switch to a single phase model. So, this may be the one here, this is start, this may be run, and that will happen split phase machine or a capacitor machine, and capacitor you can have a 2 capacitors, one way you can have a single capacitor. So, the options are, it can work, what are the options? Say start, it can have 2 phase, invariably it will be 2 phase, and run it can be 2 phase or single phase, because if you have a 2 value capacitor, this is what it will likely to happen. Okay. This is one application. So, capacitor motors, this is what it will be. There is another one which has been in use, is called as AC servo motor. AC servo motor will have a fixed voltage here, okay, and a variable voltage here. Now, what will happen is, for example, you want to open a circuit breaker, you need a motor. Okay. As soon as a fault occurs, then only it will have a voltage. If only V is permanently there, but it does not start, because with single winding there is no starting torque. only when you apply this V A which is variable. So, V m is fixed, V I is varied. Is it clear? So, when this varies, then it will start producing a torque. So, there is a it is in mostly in control system it is used, servo motors. If you have studied control systems, some they must have told you what is known as servo motor, what are 2-phase servo motors, they are quite common. You have studied this, you have done some experiments on this. So, 2-phase servo motor. Now, the typical characteristic that you expect here, the torque versus speed, since it is operating at starting. So, typically you will have a characteristic something like this, is not it? Okay. So, this mostly it is a starting characteristic. So, here the torque will be related to the voltage that you apply. If you apply more voltage, there will be more torque here, right. So, this again the you can have a program in which you can estimate the performance for different voltages. For different voltages it will have a family of characteristics, okay, different, because this V m is fixed, this is for different V A. Okay. Now, I have drawn like this. Now, this is not the usual torque speed characteristic of normal motors. What changes you see here? It has some, see, normally you would have expected torque speed characteristic something like this, is not it? It is having a very steep like this. How is it achieved? By, so sir, AC servo motors must have a rotor resistance must be very high, this is one condition. Okay. Right. So, this is and it must be quick response. Quick response means, how do you get quick response? Inertia is low inertia. Huh? Huh?
It is the bore of cylindrical, long and slender.
Long length and smaller dia. So, this is one of the things that as servo motor characteristics are low J, high R, etc. Okay. That, and sometimes they have, they do not have a squirrel cage, but they can even have a drag cup rotor. Sometimes they have a drag cup rotor, that means just a cup which is there which will be rotating, and the other core of the rotor is not stationary. So, I can make it fixed like this, because there is a stator which will be there above. Okay. So, only this is rotating. So, the conducting portion of the rotor is removed and make it like a aluminum or a silver cup. You can have a copper, aluminum or silver, and this is also being used. Okay. Since you must have studied. So, but our concern now is to look at the electromechanical aspect of the motor. Then next is AC tacho generator. Okay. I have asked you the questions. AC tacho generator, you have a main winding, you have a fixed current or a fixed voltage. The voltage in the auxiliary winding, can be proportional to the made. So, you can make VA to be proportional to the speed with IA, IM or VM constant. And you already know what is VA. What is the induced voltage VA? In that case will be JAEFM minus JAEBM, is not it, or JAIM into ZF minus ZB. So, the whole design should be such that ZF minus ZB is proportional to speed. Okay. And what happens when speed is 0? ZF equal to ZB, so therefore it is 0. Therefore, what you that means your idea is the voltage across the auxiliary winding, it should have a ideal characteristics of with omega r, isn't it? So this is achieved, one of the condition is also RR must be high. I think you must prove this, what condition in which it is this. So now you have a tool in which to estimate the performance of two phase induction motor for different applications, capacitor, split phase, capacitor motor, servo motor and tacho generator. Okay. These are typical cases that we will see. So, we will stop it here, and next class we will make what is a generalized rotating field theory, means why only 2 windings, you can have more than 2 windings, and why only at 90 degrees, it can be any angle, supposing it is at 45 degrees, how do you analyze this. So, I think this is a more powerful tool that we will discuss after the next class. Okay. We will stop it here.